Equipped with the expression of the chemical potentials for solvent A and solute B in solution, and as pure liquids, we can now calculate delta mixing G, the change in the Gibbs energy upon mixing Na moles of A and Nb moles of B. This calculation will allow us to evaluate whether the formation of an ideal solution is spontaneous or not. We define delta mixing G as the Gibbs energy for the final mixture or solution state minus the Gibbs energy for the initial or pure component state. The Gibbs energy for the mixture is equal to Na times the chemical potential of A in solution, or mu A liquid, plus Nb times the chemical potential of B in solution, or mu B liquid. Similarly, the Gibbs energy for the pure components is equal to Na times the chemical potential of pure liquid, or mu A star liquid, plus Nb times the chemical potential of pure liquid B, or mu B star liquid. Combining the last three equations, we can write delta mixing G equals Na mu A liquid plus Nb mu B liquid minus Na mu A star liquid plus Nb mu B star liquid. Now, using Raoult's law for the solvent and the solute in solution, since we are interested in ideal solution, we can express the chemical potentials mu A liquid and mu B liquid in terms of the mole fractions of A and B in solution, and in terms of mu A star liquid and mu B star liquid respectively, and obtain mu A liquid equals mu A star liquid plus RT times the natural logarithm of XA liquid, and mu B liquid equals mu B star liquid plus RT times the natural logarithm of XBL. This allows us to write delta mixing G equals RT times the natural logarithm of XAL plus NB times the natural logarithm of XBL. We can go one step further and express the number of moles of A and B, Na and Nb, in terms of the mole fraction XAL and XBL, and in terms of the total number of moles of A and B, which we denote by N. So we get the final equation, delta mixing G equals Nr times XAL, natural log of XAL, plus XBL, natural log of XBL. The Gibbs energy change upon mixing divided by nRT is plotted as a function of the mole fraction of A in solution on the right hand side. We can readily see that for all compositions, the Gibbs energy change upon mixing is negative, indicating that mixing is spontaneous. We can also observe that this curve is symmetrical with respect to XAL equals XBL equals 0.5, where the Gibbs mixing energy change is minimum. We will see on next slide that this condition is associated with the largest increase in entropy upon mixing. We now start with the expression for the Gibbs energy change upon mixing to form an ideal solution. As discussed on the preceding slide, delta mixing G is always negative since the mole fractions of A and B in solution are always less than unity, and their natural logarithms are negative. The mixing is therefore spontaneous for all chemical compositions. Where does the mixing spontaneity come from? To understand this, we will now extract other property changes upon mixing. We recall that for any process, taking place at constant temperature, we can write delta G equals delta H minus T times delta S. So for mixing, we have delta mixing G equals delta mixing H minus T times delta mixing S. We recall that at constant pressure, dP equals to 0. The full expression of dG, that is VdP minus SdT, simplifies to dG equals minus SdT. This equation implies that S is equal to minus dG divided by dt. That is, the entropy is minus the derivative of the Gibbs energy with respect to absolute temperature. So we conclude that delta mixing S is equal to minus the derivative of delta mixing G with respect to temperature. Using the expression for delta mixing G, we obtain delta mixing S equals minus N times R times XAL natural log of XAL plus XBL natural log of XBL. Since the terms XAL and XBL are less than 1, their natural logs are negative and delta mixing S is positive, which indicates that mixing leads to an increase in disorder. We now calculate delta mixing H as delta mixing G plus T delta mixing S, and easily show that delta mixing H is equal to 0. Since mixing is an isobaric process, we conclude that the heat associated with mixing to form an ideal solution must be equal to delta H and is therefore also 0. So the change in entropy for the surroundings upon mixing is equal to 0. Since the terms XAL and XBL are less than 1, their natural logarithms are negative, and delta mixing S is positive. The change in entropy for the surrounding upon mixing is equal to 0. Therefore, delta S universe has the same positive sign as delta S for the system, another manifestation of the spontaneity of the formation of ideal solutions from pure components. Using dG equals VdP minus SdT at constant temperature indicates that V equals dG over dP, from which we conclude that the change in volume upon mixing, delta mixing V, is equal to the derivative of the Gibbs energy change upon mixing with respect to pressure, or d delta mixing G dividing by dP. Since no terms in the expression of delta mixing G depend on pressure, we conclude that this latter derivative is equal to 0. Hence, there is no change in volume upon mixing. From the expression H equals U plus PV, or U equals H minus PV, we conclude that the change in energy upon mixing, delta mixing U, is equal to the change in enthalpy of mixing, delta mixing H, minus P times the change in volume upon mixing, delta mixing V. So for ideal solution, there is also no change in energy upon mixing. This is an important result as it makes it clear that the intermolecular interactions between like species, that is A and A or B and B, must be the same as the interactions between unlike species A and B.